Hey everyone, welcome to our second lesson on theoretical probability. So in the textbook, we are on section 4.2. And like I said, today's lesson is basically continuing on from what we did yesterday. So in our last lesson, we were talking about experimental probability, which is probability based solely on actual experiments that we carry out ourselves. Whereas theoretical probability, we'll take a look at this, is more about what we think should happen based on what the mathematical principles that we have. So our goal today is just to figure out how to calculate theoretical probability, and this might be a little bit of review from even elementary school with a couple of new terms that you're going to learn. Then we're going to look at comparing theoretical probability with experimental probability, and finally we're going to be looking at what a complementary event is. So just a quick recap, we know how to find experimental probability. We can find experimental probability by simply counting the number of times that a desired event occurs, and we are essentially comparing that to the number of trials that we actually have. So as an example, and I think I gave an example like this before, let's say that we have something like you're rolling a dice 100 times, and I think I've made an example very similar to this, and you got a 5 20 times. So 20 times were able to get a 5. So I'm just going to put that here. So you got a 5 there, and experimental probability is basically just comparing the number of times you actually got the 5, which is 20, to the total number of times that you actually rolled the dice, which is 100. So it'd be 20 over 100, which you can reduce as 1 over 5. So this is just an example of an experimental probability that we could look at. So up to this point, we haven't introduced a couple of new words or new terms, one of them being simple events. So a simple event is essentially an event that only consists of one outcome. So an easy example of this, if you're rolling a dice, rolling a 3, that's one of the possible outcomes, right? 1 of 6, and that's a simple event because there's only one outcome that matches up with that. And that's pretty obvious, right? Like the only way that you can have a result of 3 is if you get the side with the 3 on there, right? Whereas something that would not be a simple event, and this is actually called a compound event, you don't have to worry so much about the terminology yet, but just letting you know, compound event would be when you roll 2 dice, and let's say that we're finding the sum of the 2 numbers. Well, in this case, having a sum of 3 is actually not a simple event because there's actually 2 results. In this case, there's actually 2 outcomes that match up with that result. So for example, I could have a 1 and a 2, and actually I said a different order, 2 and a 1, or I could switch it around, right? I could have a 1 on the first dice and a 2 on the second dice. So there are 2 different ways that I could get a sum of 3. So these 2 obviously add up to 3. These 2 obviously add up to 3. So just kind of keep that in mind, that that's the difference between a simple event and a compound event. So that's just terminology. Just want to make sure that you're familiar with that. So what is theoretical probability? So theoretical probability, we talked a little bit about this, but now this is the formal definition. Essentially, it's probability based on the mathematics, right? So based just on mathematical principles where we assume all the outcomes are equally likely. This is probably the most important thing to understand. We assume that they're all equally likely. So on a dice, we have 6 sides. We know that when we roll a dice, we're not always going to get the same amount every single time, right? We're not always going to get the 1s as many times as the 2 or the 3 or the 4 and so on. But mathematically speaking, because there are 6 sides, all 6 sides should be coming up the same number of times. So that's what theoretical probability is based on. It's based on the fact that all the outcomes should have the same chance or probability of occurring. So again, the biggest thing that I can say here, and you might want to underline that word, it's based on what should happen. That's the key word, should. Doesn't mean it actually will happen, but based on what should happen. So how do you find probability, a theoretical probability? So this is actually quite easy. You take the number of outcomes that match up with event A, so however many outcomes match up with event A, and you divide it by the total number of outcomes. And when we talk about outcomes, it's all the possible results of the experiment. And again, we will often assume when we are calculating theoretical probability, we assume that the experiment is fair, which means all of the outcomes are equally likely to occur. Just keep this in mind that it does change. It's not always going to be fair. So for example, you could have a dice that for some reason Maybe someone decides to put a little bit more weight on one side, right? So it's a fixed die in that case, right? So that's an example of something that's fixed or it's biased towards one result. And if that's the case, then that means that one of the sides has a higher chance of occurring than another one, right? So just kind of keep that in mind, that we often assume in questions that the experiments are fair. So proper notation. So this is just going over a lot of the notation that we have in math, especially when we talk about probability. So we have one little notation here, NA. So N and then in brackets A. What does that mean? So what that means, it's the number of elements in this set. So we're talking about set A. It's almost kind of like functions, right? Just like with functions, we had f at x, and that basically means what's the value of the function at x. We're basically saying what is the value, how many elements are there in this set A? So the set A, how many elements are there in there? And the A itself, or that we're looking at in this case, is called our event space, which is essentially all the outcomes that match up with event A. That kind of makes sense. So going back to that example about the event being, so I'm just going to write this down. The event was the sum of 3. Oops. So we know that there are 2 outcomes that match up with that, right? This outcome matches up with it, and this outcome matches up with it. So there's 2 different outcomes that match up with it. So these 2 that we have here, these 2 outcomes together are part of the event space. The sample space is represented by S, and the sample space is essentially the collection of all the possible outcomes, right? Every single one. So every single combination we can think of, right? Anything that's come up. So when we write NS, what we're saying is we're basically saying the number of elements that are inside of the sample space. So the sample space is the broader set. The event space is a smaller set. So if we want to find out what the theoretical probability is, really what you're doing, and this is nothing new, this is basically a repeat of what we already said. All we're doing is essentially just taking the number of events that are the number of outcomes or elements that are in the event space and dividing by the number of elements that are in the sample space. That's all we're doing. So we're just dividing the number of outcomes that match up with A by all the possible outcomes of the experiment. So how do we use this proper notation? Let's look at an example here. And in this first example, you're probably going to be like, why am I going into so much detail over a pretty easy question? But the reason I'm doing this is just so you're familiar with the terminology. So in a standard 6-sided die, what is the theoretical probability of rolling a 2? So I'm pretty sure everyone can probably figure this one out. You probably have done questions like this in elementary school. But before we even get to that, let's just answer the first 2 things here. Events, what is the event space and what is the sample space? So what is the event space? Well, the event space is all the outcomes that match up with the event that you want, which is rolling a 2. So in this case, this is going to sound really obvious, but the only element there is 2, because the only side that actually matches up with the event of rolling a 2 is this one right here. It's only one. So again, really, really obvious, but we have to state that, right? So we say that the set A is basically just 2. The sample space is 1, 2, 3, 4, 5, 6. So why is it 1, 2, 3, 4, 5, 6? Because those are all the possible outcomes that you can get when you roll the die, right? So we just list them all off. So when I ask for the list of outcomes, or the sample space in this case, I want you to actually list them all off, right? Now to find the probability, all we're really looking at is how many elements or how many items are there in the sets. Well, how many items are in this set right here? There's only 1. Obviously, right? And how many elements are in this set? There's 6 of them. So that means that the number of elements in A is 1, the number of elements in S is 6. So that means that the probability of rolling a 2 is simply NA over NS, or the number of elements in A, which is 1, over the total number of elements in the sample space, which is 6. So that ends up giving us 1 over 6. And that's all we have to do there. Let's look at an example here, deck of cards. So let's say that you're picking a card from a deck and you want to find the probability, or you want a king. What is the theoretical probability of selecting a king from the standard deck of cards? So in this example, first thing before anything else with cards, if you have played card games before, you're probably familiar with all the deck and all the cards in there. In case you are not, I decided to just include a little picture here for you. I would definitely take a screenshot of this or have a picture of a deck of cards. I'll always try to include that if I can on a test if you ever need that. But for now, I would recommend that you just keep a screenshot of it, just so you have a reference to this. So in this case, we have our total, all the possible outcomes when we pick a card from a deck, and there are 52 cards here altogether. And a little bit of math here. How is it created? Well, we have 4 of each type, and there are 13 or 4 suits basically, and then there's 13 of those types of cards. So 4 times 13 would be a total of 52. So in this case, we are interested in finding the probability of choosing a king. So there's actually 4 outcomes that we're interested in. So there's this one here, the king of spades, king of spades, king of clubs, king of hearts, and king of diamonds. So these are the 4 outcomes that we're interested in. So the 4 outcomes there, we are going to divide that, and I actually drew it out there for you as well. We're going to divide that total number, the 4, by 52, because there are a total of 52 cards. So that means the probability of you choosing a king would simply be 4 out of 52. And this is fine if you leave it like this, but we already talked about this. When we have fractions, we always want to reduce as much as we can. So if you divide both of them by 4, you end up getting 1/13. And that's the probability of choosing a king. So let's look at another example here. So for the same deck of cards, let's look at the probability of each of the following events. So let's start with the first one, picking a 9. Then picking a red card, and then last we'll look at the probability of picking a spade. So the probability that I pick a 9, well, how many 9s are there? So we can go back to our picture to help us out. So let's just scroll back a little bit. So how many 9s? We have 4 9s, right? So the 9 has all 4 suits. So that means that we're going to have 4 cards that are 9s, and it's going to be 4 out of the possible 52. So 4 over 52, and I wrote 42, my bad, and I can change that typo later. 4 over 52 gives you, is reduced to 1/13. For the next one, picking a red card. Well, how many red cards are there? So we can go back to the picture just to make sure. If you're not familiar with the deck of cards, it's actually pretty easy. It's pretty visible even just on the picture here that we can see that half of them exactly are red. So the bottom half is red, the top half is black. So that means that there are going to be exactly 26 red ones out of the 52. So 26 out of 52 reduces to a half. And the last example, what's the probability that I pick a spade? Well, how many spades do we have? So if we go back to our picture, and again, I'm just going back for everyone in case you're not familiar with the standard deck of cards. So the spades are the ones right here in the second row here, and we can see there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 out of the possible 52. And so 13 out of 52, when you write that out as a fraction, you reduce that to 1/4. So let's look at an example with the spinner. And actually, we have already seen this example, but I wanted to revisit it from a different point of view. So in the previous example, so from the last lesson, we were looking at the experimental probability of this spinner landing on blue. Now we're looking at the theoretical probability of it landing on blue. So what do we have to do for theoretical probability? Well, first thing, we need to count how many outcomes there are. And there are a total of 1, 2, 3, 4. Oops, and you can't even see that because it's covered in the red. 4 outcomes that are possible. So of those 4 outcomes that are possible, only one of them, which is this one over here, is the one that we actually want, the one we're interested in. So that means the probability of us choosing a blue is simply 1 out of 4, which reduces to 25. Well, we can leave as 1/4, or we can write as 25%. So the reason I want to compare this with the last lesson is because when we did experimental probability, if you look back at your notes, we actually found that it was 40%. So you're probably wondering, why did I have 2 different answers for probability? Shouldn't probability always be the same? Well, it depends on which type of probability we're looking at. In this case, we're looking at theoretical probability. So according to math, we should land on blue 1/4 of the time, or 25% of the time. But according to the experiment that we did in the last lesson, we actually landed on blue more times than that. We landed on it 40% of the time. And there's a reason, there's a difference here. They're actually, even though they both measured probability, but they measure it in a different way. So what is the difference between them? So experimental probability is essentially, theoretical probability, I'll start with that one first, is the likelihood of an event occurring based solely on math. And I know I'm repeating this, but I just want to make sure that you really, really understand the difference here, okay? So that's based solely on math. So we're not looking at, we're not actually carrying out an experiment ourselves. So if you saw in the last couple examples, we did not do any sort of simulations. We did not get a virtual dice or a virtual coin, none of that, right? We did that in the last lesson. We're not doing it now because this is based solely on math. And we assume all the outcomes are equally likely to occur. Whereas experimental probability, you actually have to do it, right? You can't just say, oh, it's supposed to happen 1/4 of the time. You actually want to perform that experiment in order to find out if that's true or not. So it's a little bit different. So I hope you understand the difference between them. And the biggest thing I can tell you when you're comparing them is that the theoretical probability is always going to be the same. It's never going to change. Theoretical probability doesn't change depending on what your friend calculated and what you calculated. Idea, if you're both doing it right, it should always be the same. Whereas experimental probability, there's actually multiple answers, right? Because it depends on the actual experiment that you carried out. So you may have tossed a coin. You may have tossed a coin 100 times and gotten heads 60 times. But maybe your friend tossed a coin and only got heads 40 times. And it's not like you're right or he's right or she's right. It's just randomness, right? It's an experiment that you carried out, and you know that it's not always going to be the same result all the time. But theoretically, according to math, it should, if you toss a coin 100 times, you should be getting heads 50 times. Hope that kind of clears it up. Okay, so we're near the end of the lesson here. I just want to go through a couple more things. The law of large numbers. So the biggest thing, so I've already mentioned this, the experimental probability and theoretical probability are different. However, if you do it enough times, they actually will be pretty close to each other. And this is actually what the law of large numbers says. It basically says that the more times you perform an experiment, the closer the experimental probability will be to the theoretical probability. So going back to the coin example, if I'm tossing a coin, I know I have two outcomes, right? Heads or tails. If I were to toss it 10 times, I think everyone knows this, it's not weird if you didn't get 5 and 5, right? Like, it's actually normal. It would be totally normal. It's not like you would be like, oh, that dice is fixed. Like, there's something wrong with that dice if you didn't get 5 and 5. You could have 4 and 6, or the other way around, or you could have 3 and 7, different variations of it. And anything here would be, for the most part, pretty acceptable. But if I did this 1,000 times, or even more, like 10,000 times, I really should be getting pretty close to 50-50 here. I shouldn't be having one outcome a lot more proportionally to the other one, right? They should be pretty close to each other. So as an example here, and I have just a quick example with the coin. If I were to toss it 20 times, and I already mentioned this, it's pretty normal for us to not get exactly half and half. We shouldn't be getting half heads exactly and half tails. If you do, great, but it's not necessarily going to happen, right? And I think everyone can accept that that's normal, right? There's nothing weird about that. But if you were to toss it 1,000 times, 10,000 times, 1,000,000 times, and you for some reason got 1/3 of the time, this is just an example, this would be extreme, and then you got the other outcome only 1/4 of the time, that's weird, right? Because they really should be quite close to each other. So eventually, even though the probability of getting heads may change depending on the experiment, and the probability of tails will also change as well, eventually, both of these probabilities should go towards being the same, which would be 1/2 and 1/2, right? So eventually, the theoretical probability, the experimental probability should eventually match up with the theoretical probability. They should get closer and closer to each other the more times you do it. And that just kind of makes sense. The more times you do something, the more accurate it is, and the more true it is to what mathematically should happen. So, and going back to that last slide, I'm not going to go back to it, but just making a connection between probability and data management and statistics specifically that we're going to cover later on. This is going to be huge when we talk about collecting data from people, right? When you're collecting data, you really want to make sure you're getting a lot of it, because if you're only collecting a couple surveys, that's not really giving you the true picture. But the more times, the more you collect data there, the more accurate it's going to be. And that's a perfect example of how your accuracy will improve the more times you do it. So probability involving compound events. So we're just looking at what happens when two experiments happen at the same time. So rolling two dice at the same time or tossing two coins at the same time. So in this first example, you have, we're looking at a board game and you're trying to find out what is the probability of me rolling a sum of 7. So keep in mind, it's a probability of rolling a sum of 7. It's not, so we're not talking about one dice. Now we're talking about two dice. And essentially what we want to do is find out what's the probability that the two numbers that we end up getting and add up to 7. Well, there's lots of different ways you can do this. You can either try to list it all out, which would take you a little bit of a while. I would recommend something called a tree diagram. We haven't learned that yet. But for now, honestly, I think the easiest thing to do is just start as much as you can. Just start thinking of all the possible outcomes here, even though it's a little bit long, but we haven't learned about tree diagrams yet. We'll do that later on once we learn it. But all you can do for now is just start matching them up, right? So we have 1 and 1, 1 and 2, 1 and 3, 1 and 4. Just start writing down as many as you can think of. 1 and 5, 1 and 6. So we did all the ones. Okay, well now let's do the next one. Now let's do 2. 2 and 1, 2 and 2, 2 and 3, 2 and 4. Oops, that's a 3 there. 2 and 4, and so on. I'm not going to complete this all for you. But essentially, you can list them all out. Or there's something, probably might be a bit of a better way to do this, is to track it through a table. So what you're going to notice is that you can almost create, it almost looks like a multiplication table. You're matching up all the possible outcomes together. So if we end up creating this table, we'll see that there are a total of, and just do a little math here, 6 times 6, 36. There are 36 different outcomes. So what we want to do now is just count how many of those outcomes have a sum of 7. So just my apologies, just got to get an eraser here. I got a new device, so I'm still learning how to use this one, so I apologize. Okay, so what we're going to do is we're going to go to our table and we're going to try to figure out how many of these outcomes add up to 7. So which ones add up to 7? Let's see. So we have 1 and 6, 1 and 6 adds up to 7. So there we go. 2 and 5 adds up to 7. 3 and 4 adds up to 7. 4 and 3 adds up to 7, and so on. And obviously, I made this one a little bit easier for you because I already did the table with the sums included in there. But you could always do this yourself. It's pretty easy to fill in. And then what do I see here? I have a total of 1, 2, 3, 4, 5, 6. I have 6 outcomes that 6 different outcomes that give me a sum of 7. So because I have 6 of them out of 36, that reduces to 1 over 6. So the probability that it roll a sum of 7 is 1 out of 6. And now let's look at the next part. It says, what is the probability of rolling a 2? So rolling a 2 here, let's see how many of these outcomes give us a sum of 2. Well, actually, there's only one. This is actually called the snake eye, in case you're interested. You probably heard of that, and maybe some games, if you ever played any card games or any games involving dice, sometimes they talk about snake eyes. That's what that means. So when we have a 1 and the 1, that gives us a sum of 2, and that's only one outcome out of 36. Let's look at another example, tossing 3 coins. So if we toss 3 coins, again, we're going to be looking at what are all the possibilities first. And then the second part of the question is asking us, what's the probability that I get a 1 tail? So how do I list out all the possible outcomes? In this case, I would say it's a little bit easier. It's easier to think about all the possible groupings. So what I would do first is I would maybe make 3 little lines here and just keep track of all the different combinations. So let's start with something easy. I know I could have heads, heads, heads. I know I could have 2 heads, and then maybe the last one is a tail. I could keep the two heads, but maybe what I'll do is I'll put the tail in between. So it'll be heads, tails, heads. Or I could do the tail at the beginning and then put the heads and the heads. So I'm just thinking of all the possibilities here. So far I've considered if it's 3 heads. I considered here if it's 2 heads. Just kind of listing out all the possibilities. So I obviously I totally missed the possibility of only 1 head. So what's the possibility, how many outcomes are there for 1 head? And I'm just gonna make a little bit of space here. So for 1 head, I would have a heads and a tail and a tail. I could have a tail and then the heads is in the middle, or I could have a tail, and then a heads. And then the last possibility here is just tail, tail, tail. I hope that kind of makes sense. So that is going to be, and I'm just counting them out, making sure it all makes sense. These are the 3 possibilities if I have the 3 heads, right? And this is the only one, the only possibility when there's all 3 tails. So altogether, how many possibilities do I have? I have a total of 8. And again, you can do this however you want. You can either list it off or you can use something called a tree diagram, but we haven't learned about that yet. So what I did is I simply just wrote it out, and these are all my possibilities here. So in the second part of the question, they're asking us, what's the theoretical probability of getting exactly 1 tail? So let's look here and let's circle all the ones that only have 1 tail. Well, that's 1, 2, and 3. So there are exactly 3 out of the 8 that give us exactly 1 tail. So how do we write that as in terms of probability? We write it as 3 over 8. So let's look at complementary events. This is the last new word that we're going to learn here. So complementary event is essentially a set that we contrast with the set A. So set A is simply just a set of it's a set of elements that collectively match up with the event A, right? And when we look at the complement of A, and we use this terminology here, A, and then there's a little apostrophe there. What we're essentially saying, it's the set of all the outcomes that are not in A. So A is obviously the event that we're interested in. A with an apostrophe, which represents the complement of A, is all the outcomes that are not in A, okay? So in terms of probability, what that really means is if you're not part of the event A, then you would be part of the complement of A, essentially, right? So we know that if we add up all the probabilities of all outcomes in an event, they should add up to 1. And there's a reason for this. They have to add up to 1 because, of course, when we add all the possible outcomes together, we should get 100%, right? We included all the different outcomes, so if we add them all up, we get 100%. They're all included in there, right? So the probability of you being in the complement or some outcome being in the complement, you can easily find that by simply taking away the probability of an event occurring. So this seems a little bit complicated, but I think when you look at an example, it'll make a lot of sense. We're essentially just saying that we're taking away the probability of A occurring from 1. So let's look at a quick example here. I think it'll make a lot more sense when we look at something more concrete. So a bag contains 12 marbles, 3 of which are blue, 5 of which are red, and 3 of which are green. So what is the probability of choosing a red marble? And then the second part, what's the probability of not choosing a red marble? So let's start with the first part. So the probability of choosing a red marble is simply going to be 5 out of 12. And why is it 5 out of 12? Because there are 5 red ones, right? Which is the number of marbles we're interested in. And there are a total of 12. So that means the probability of choosing a red is 5 out of 12. For the second part, it says, what is the probability of not choosing a red marble? Well, if we want to find the probability of not choosing a red marble, we have 2 options. We can either take the number of marbles, that are not red, which is the blue and the green, and we can add them up, and that gives us a total of 7. And we can take that 7 and divide by 12, right? Because that's all the possible outcomes you have. Or the other thing we can do is use the principle that we just learned. We essentially said that we can, if we know the probability of choosing a red, to find the probability of not choosing a red, we just take away this probability from 1. So there is 2 possible ways to do it, and I'm going to show you get the same answer either way. So we know that the probability of not choosing a red, we already said this is 7 out of 12 because there's 7 that are not red out of the possible 12, or we can simply subtract 5 out of 12 from the 1. And if we do this, if we take away 5 out of 12 from 1, and I didn't show the work here, but if you're just need a little recap of fractions, let me know. I can write this as 1 over 1 minus 5 over 12. You find a common denominator, which is 12 over 12 minus 5 over 12, and obviously 12 over 12 minus 5 minus 5 over 12 is 7 over 12. So that's my final answer there. Okay, so hopefully that explains how we use that theory. So that's it for the lesson. Here's the classwork. So as always, please keep up with the work and post any questions for the online virtual cohort. Please post any questions on the discussion board. And for the ones in class, please ask for help. Okay, thank you so much.